Hi guys and girls. As you can see today, I am not in school, and as a result, I put together this video to finish up our Metamorphic Rock information. So you can see I'm looking here at the study guide, and this is going to be on page 18 on the bottom half. We only have about 2.5 or so little pages to go through, and you're going to follow along with your study guide while I narrate on this video. When I'm done, I'll have a second video posted um, on your note screen that will show you a quick review of the three different rock family organizational systems, such as the igneous, metamorphic, and sedimentary. So let's begin here with metamorphic. And I should say, at any point, if you need to pause this video so that you can continue to write, or you can rewind and replay at any point, that's perfectly okay. So here we go. Metamorphic rocks. I think you studied this in 6th grade, so this should be a bit of a review from you. But these are rocks that are going to have formed from other already pre-existing rocks. So if we can have sedimentary or metamorphic or igneous rocks that already exist, they're going to be exposed to heat and pressure, and they're going to change. So one of the key words for any igneous rock, metamorphic rock, one of the key words is going to be changed. And if we look at this picture down below, the way that the change occurs is through the application of both pressure and heat. Generally speaking, heat and pressure. So if you look at this picture, we're seeing that down here we have a magma plume that's going to, of course, be incredibly hot, molten rock. And we're really realistically talking about a depth that is going to be very, 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 very deep. So this is going to be very likely several miles deep. And if you think about what that means, the weight of rock overlying for miles is going to be incredibly powerful and strong. And that downward pushing force generates a squeezing pressure on those rocks. In addition, from underneath, the deeper you go, the hotter it gets. So down from underneath, we're going to have magma that's pushing its way upwards and providing a heat source. So when rocks get really, really heated, we're not talking, in this example, for metamorphic rocks, we're not talking about rocks being melted, but they get sort of semi-melted, kind of gooey. I like to use the Halloween candy analogy. So many of you went Halloween trick-or-treating the other day, and let's say you come to school with a chocolate candy bar in your pocket, and you're going to eat it a little bit later on. And what happens to that candy bar throughout the day as it sits in your pocket and is warmed by your body temperature? That candy bar is going to start to get kind of gooey and soft and mushy. That sort of gooey, soft, mushy, it hasn't changed the candy bar other than its flexibility and squishiness maybe, but it's still the same basic ingredients. So metamorphic rocks are like that. They're being heated, and that heat allows them to get squishy and gooey and soft and flexible. And in that environment, minerals begin to grow once again. Sometimes minerals that were already there will take off in growth and get bigger. Other times, minerals that didn't used to exist begin to grow because of this presence of heat and pressure. It's a new environment, and it might just be the right scenario for something brand new to start growing. So because of pressure and heat, we're going to change and alter rocks deep within Earth. So the three things that we look at for the conditions to form metamorphic rocks are, of course, heat, pressure, and chemical activity. That crystal regrowth involves, using my Lego analogy once again, kind of taking apart the molecules and putting together into different ways, taking apart the Legos and putting them together in different combinations. That results in different mineral development within the rocks. If we jump down a little bit to this paragraph right here, it says, under conditions of high temperature and high heat, many metamorphic rocks form by the process of recrystallization. That's a key word we have to know. Crystallization means from molten material we're forming crystals, and here recrystallization means new and regrowth, and new different crystals are beginning to grow. This is the growth of new mineral crystals from the sediments of a sedimentary rock, or the growth of new mineral crystals from the crystals of an igneous rock, or, of course, metamorphic rocks. So even metamorphic rocks can be remetamorphosed. You might imagine that being exposed to massive pressure and heat in the regrowth of crystals might severely alter the rocks, and in fact it does. Some of these alterations are going to include increased density. Because of the pressure and the depth, these rocks are really being squeezed and compressed and compacted, so they're much more dense. New minerals are going to grow. Oftentimes minerals that didn't used to exist will grow. Some minerals only grow in really, really deep, high-pressure environments. So maybe a sedimentary rock that formed in the shallow surface of the earth will now undergo growth of new minerals that didn't used to be there. And oftentimes we get what's called banding. I'm going to show you this in a little bit later on your reference tables. But if you look at this picture to the right, we see kids oftentimes call this the zebra rock. And it has this striping effect to that. We call that banding. Not to be confused with layers from sedimentary. But these bands are a result of the pressure applied to that rock while it's recrystallizing. And then also, number 4, sometimes structures that were already present, because of the intense squeezing, are going to get distorted. So in this picture, we see this kind of twisting and bending. These might they might have been sedimentary layers that are now kind of baked together, but they get twisted and mangled up because of the intense pressure resulting from the depth that they form. And then our last page here, I want to take a quick look at the organization of all the different minerals and where we see this on the reference tables. Again, anything on the reference tables is not memorizable material. You just need to know where to find it. So metamorphic rocks come in 2 different forms. We have foliated, and foliated metamorphic rocks means that they have layers or bands. And also layers is in quotations because they're not truly layers. Only sedimentary rocks have layers. But these are rocks that are going to develop some kind of mineral growth that's going to be sort of aligned, so that if all the minerals are growing in this direction, they all are sort of parallel to one another, and that produces an overall striping, banding pattern on those rocks. Are non-foliated, or just as that name implies, they're not foliated. They do not have bands or crystals. These tend to look a lot like igneous rocks. They tend to be maybe 1 or 2 colors. They're very crystalline looking. They look very igneous. In fact, they can be kind of hard to distinguish from igneous rocks. So in our little organizational chart down here, these are examples of foliated rock: slate, schist, and gneiss. This is pronounced gneiss. You may have heard of some of these. Probably slate you have heard of. The blackboard, in fact, in the back of the classroom is slate. It's a very low level. So the way this works is these examples are sort of from a low to a high metamorphism. So as we come down the chart here, we're getting more and more and more metamorphosed. And I think of it almost like a food analogy of cooking. So slate would be a very sort of low level, just a little bit of cooking. And then a schist is a medium, and a gneiss would be a very high level metamorphism where lots of sort of cooking has occurred, if you will. Lots of heat, lots of pressure. It's well done. And if we look at some of the original rocks that became these things, shale very much is a sedimentary, well, it begins as a sedimentary rock. It actually starts out well, shale is a sedimentary rock, and that becomes slate by the heating, cooking nature. Shale is made by clay pressed together. And through the application of heat and pressure, now that shale clay molecules are actually going to be fused together. Again, a candy a candy example, if you will, from Halloween. If you have a bag of loose candy, loose chocolates, and like chocolate chip kind of things, and you have them in your pocket, they're going to get soft and gooey. And if they get to the point where they're nearly melted, they're really squishy and gooey, and they're in your pocket getting kind of pushed and smushed together, Then you find it, you take it out. Oh no, I have this chocolate bag. You take it out and you put it on the table, and then it cools down. Now all these little individual sticky particles are stuck together in one sort of a lump. So shale is clay that's pressed together, like chocolate that's just kind of in a bag together. And then um, metamorphism is when you add enough heat to kind of begin to melt them. They can't truly melt. Any rock that melts becomes liquid, becomes igneous. So we're talking clay particles here that get partly melted, get soft and gooey, and they stick together now, and they're actually fused together. That's much stronger than a sedimentary rock that's simply pressed together. In a snowball, if you squeeze snow together, you make a snowball. If you squeeze snow together, dunk it in water, and let liquid water actually freeze and bond all the snow grains together. Now you have an ice ball. That's much more like a metamorphic, where it's been actually fused the particles together. An example of a schist very often comes from slate, and slate over here is a metamorphic rock. So shale could become slate, and if it keeps going, could become schist. Schist is kind of cool when you see that in lab. It's very sparkly and kind of space age looking. So it used to be a metamorphic rock, and it's going to be now even more metamorphosed from a low to a medium level. And then ultimately, gneiss is the top end. And very often, granite can become gneiss. Granite that is really super deep inside the earth, that has taken an incredibly long time to cool from magma very, very deep in the earth, could over time also transition from granite rate keep on going and become a gneiss. This is the zebra rock, the striped kind of rock. Our other kind of rocks are the non-foliated. I'm sure you recognize some of these. Marble is a very common one that people are familiar with. You probably have marble in your home. Um, Oftentimes we have marble on floor tiles and maybe in the bathroom. It's used for statues and things like that. It's a little bit soft, but it's a very pretty rock. Quartzite is, as the name implies, has lots of quartz in it. And then coal. This is a very high-end, very quality coal. You learned in sedimentary that there's a rock called bituminous or soft coal. It's kind of dirty. It smokes a lot and doesn't make a lot of heat. This is a very high-end coal. It's very shiny and it looks partly melted, and it burns really, really hot. It doesn't smoke too much. So this is actually a very clean coal to burn. So these rocks do not have any banding or striping. And here's what they used to be: limestone. If you think about what that was in sedimentary rocks, this is coral. This is a rock that was made of tons of fossils and shell fragments and tons of life all pressed together. That becomes marble, a very beautiful, pretty rock. It's quite a transformation. Quartzite used to be sandstone. So someplace that used to be a beach, that sand gets buried and pressed together. It can be any color. And then if it gets partly melted and the sand grains get fused together and stuck together rather than sort of glued or cemented together, it becomes quartzite. Quartzite is very, very hard, very strong metamorphic rock. And of course, coal, sedimentary bituminous coal, if it's buried and deep enough within the earth and heat and pressure applied, it can partly melt and it fuses everything together and becomes a cleaner coal, an anthracite coal. So let me flip over finally to the metamorphic rock scheme in your reference tables. And again, if you need to pause this so you can take out your reference tables, that's fine. Let me show you where we find all of these things. You may have to go back and rewind or look back and forth between your two pages, and you should do that so you know where to find everything. So we have our two groups up here, our two textures, our foliated and our non-foliated. Remember, our foliated were the ones that show banding or striping or what's called mineral alignment. Again, the reference tables does a really nice job of defining for you what foliated means. The reason they're segregated into two different groups is the banding is a really high end. This is extreme metamorphism. Where the mineral alignment is more just a low end, a little bit of sticking together of the minerals. We have fine grain all the way to coarse grain. So here the minerals are getting larger and larger and larger as we come down the chart. These composition bars show us the kind of minerals that we find in them. So For example, mica. This is that very flat sheet-like mineral that can be either clear or black. We find that in pretty much all metamorphic rocks. And for that matter, we find it in many, many, many igneous rocks too. Quartz, however, tends to only be in the medium to coarse. And the reason is that the fine one up here, this tends to be slate. Slate pretty much only comes from shale. Shale is shale is a sedimentary rock that is made of clay. And clay might have some mica in it, but it does not have any of this other stuff. So all these minerals then can be found in these other examples here: phyllite, schist, and gneiss. And again, you see this arrow descending down here. It says heat and pressure increases. So the deeper, deeper, deeper down we go, the deeper in the Earth's crust, the greater the amount of heat and pressure, the greater the amount of change that occurs. Ultimately, the highest grade metamorphism rock you can get is going to be gneiss. The bottom half of the chart are non-foliated rocks, and these tend to be mostly fine on the upper portion here, and on the bottom these tend to be larger in crystal sizes. You can see the compositions. This is coal, anthracite coal, and coal is purely carbon. Um, these other things, hornfels and quartzite, sometimes they have specific compositions. The bottom few, quartz makes quartzite, sandstone. Sandstone is mostly, sand tends to be very, very, very rich in quartz, and so we get quartzite from that. Where marble used to be limestone or dolostone. These are rocks that are formed from sedimentary, either living things like shells and coral, or from some of the mineral that's in the water that fish and coral would use to make those shell and hard parts. So we talked about that in class a little bit. Calcite or dolomite are minerals. They make marble. And then finally, if you had a conglomerate was a sedimentary rock that had big things in it, like pebbles and cobbles and sand and a whole mixture of stuff. Well, that can be metamorphosed too, and you get metaconglomerate. So that's just a very quick overview. And I hope you find this too, that if you read your reference tables, you find a tremendous amount of information. Notice we have this word regional. Regional means heat and pressure. And then down here we see regional. Okay, again, that means heat and pressure. Down here, again, regional. But then we see this word contact. Contact is going to mean that it's only heat, and that's what they're telling you here. The reference tables is defining contact in metamorphism is heat only. Imagine there's a volcanic eruption, and that lava flowing down the slope of the mountain is really hot, and everything it touches, it's going to cook. Everything it touches, it cooks. Everything it comes in contact with, it will cook. So contact metamorphic rocks tend to be shallow. They tend to be rocks that are not super deep. But we see that here in the description. Heat from nearby magma or lava. This stuff is so hot that it penetrates into the rock, and the heat will start to metamorphose everything that gets really close to it. And these bottom rocks are much the same. They can be both regional or contact, either or. So this time, you're going to have a little bit of extra time. The next video I would suggest you watch, I'm going to go over the quick review of the 3 different charts for igneous, sedimentary, and metamorphic again. And at the end of that, you're going to have a little extra time left over that I'd recommend you start your homework. If you have 2 homework assignments you could be working on, either the 2.2, that's all about rocks, or the Unit 2 review, which is about the rocks and the minerals. So those are 2 things you can get started on right away. Use your study guide, use your reference tables, and I will see you on Monday. Have a nice weekend.